We can start the afternoon program. It's my pleasure to kick off the afternoon session, the title of which is Advancing Green Chemistry Education at UC Berkeley and Beyond. So we have three speakers in this session. We have our own Dr. Michelle Dusky, we have John Warner, and we also have Bill Tolman from Minnesota. Let me give you a little bit of background on each of them. I'll work in reverse order here in terms of their speaking here. So Bill Tolman, he's head of department or chair of the department, one of the two. He's the boss at Minnesota. He's a Berkeley PhD. He did his PhD here with Peter Volhart in synthetic organometallic chemistry. He's the distinguished McKnight University and L.I. Smith professor at Minnesota. He's also a co-PI on a new NSF Center for Chemical Innovation in biodegradable and renewable polymers. And the focus of his work is not just in biodegradable polymers, but also he's an expert in copper chemistry and bioinorganic chemistry. And he's also one of the members of the Faculty Advisory Board for the Green Chemistry Commitment. Dr. Michelle Dusky, another Minnesota connection, PhD from Minnesota. She's a lecturer in the chemistry department at UC Berkeley, where she does outstanding work in freshman chemistry in Chem 1 and Chem 4. I've worked with Michelle now for the last 3 years in freshman chemistry, and she's an incredibly valuable member of that teaching team. She's taking on a role now in developing the new labs that we have in Chem 1 and Chem 4, which is our majors course. And so she'll talk about those efforts at UC Berkeley. And we'll start with John Warner, who obviously needs very, very little introduction from me. He's a god in this field, obviously. He's a god, so there's more than one. He's a chemist. He got his bachelor's degree from UMass Boston, PhD from Princeton in medicinal chemistry. Author of many, many papers. He also runs the Warner Babcock Institute, with doing research on applications ranging from electronic and polymeric materials to pharmaceuticals and cosmetics. So we have a great panel discussion in store here. We'll let each of the panel members talk for as long as they want, up to about 20 minutes. And then they'll all come and sit up here. I'll ask a couple of questions, and then what I'd like to do is, assuming we have lots of time, give more time to the audience to ask questions. I know we were a little rushed this morning. I think we'll have a bit more time this afternoon. So let's start. And John, would you like to come up? And let's give John a warm welcome here.
Well, hi, I'm a little intimidated by, I am oftentimes referred to as a god, but it's usually, oh God, are you here again? But, thrilled to be here. Berkeley is obviously doing amazing things. We've heard some of the things. I think in a workshop conference like this, we just get the tip of the iceberg and see, some of the great things that are going on. But obviously, there's so many people involved in what's going on here at Berkeley. It's almost fractal, and that every time you look at it, it gets even more interesting and more complex, and they've just figured it all out here, and it's so great to be part of this program and to be supporting the work that everyone's doing here. What are we doing here? Chemistry is a funny thing, isn't it? If I'm at a party and we're hanging out with a bunch of people and someone says, oh, what do you do? And I say, I'm a chemist. Okay, it's almost like a movie. You hear the scratch of the record and everyone stops and then finally the breaks up and people start talking again. And say, I realize that this is not a good conversation starter. So now what I do is I say, oh, I'm a molecular designer. And they go, oh, how interesting. But the word chemistry has some interesting interesting connotations to it. And I think that that's a problem. You know, what usually happens is people go, oh, I hated chemistry in high school. Ooh, chemistry. What happens to a society that abdicates any responsibility to some field of science if we have this allergic reaction to chemistry, when we're buying products in the store, when we're voting for politicians, when we're reading newspapers and stories about toxicity, environmental impact, and the people reading it say, oh, I hated chemistry in high school? We got a problem with communicating to the general public these pretty complicated issues. I would argue, hope I don't get beat up here, I would argue that chemistry is no more difficult than any other subject in high school. I think, sadly, it's one of the most poorly taught subjects, but it's not the most difficult. And for whatever reason, we've evolved that we don't do such a good job in educating chemistry at certain grades. Okay, I think that there are certain children that are destined to become chemists, and we do a great job facilitating that process. But I don't know that we do a great job at attracting people to chemistry that otherwise wouldn't. And if innovation and creativity is about interdisciplinary stuff and looking at how these fuzzy interfaces work, isn't it critical for a sustainable future for us to be attracting the people that wouldn't normally go into chemistry? Think about it. If you've got some wide-eyed 12-year-old kid that says, I want to grow up and save the world, is chemistry on the top of the list of disciplines that they're going to go into? Probably not. But I think we'd all agree it has to be. Who's going to invent the better materials? Who's going to invent these things? So at the end of the day, the communication of the need is critical, and we're doing a very good job at that. But meeting that need and creating a supply chain of scientists dedicated to these solutions is still kind of eluding us. Okay, and we need to get better at that. And that's why what's so important here at Berkeley is that not only is it amazing world-class research going on, but they're bringing it into the curriculum, they're bringing it into the education, and they're tying it together. It is my experience. I honestly feel that we have done a good job in the last 20 years making the case for green chemistry. I think that companies recognize that green chemistry is smart chemistry. By my definition now, green chemistry is something that is got superior performance, superior cost, and better environmental toxicological importance. Who would turn that down? Okay, performance, cost, and an environmental benefit. I would argue, you know, people talk about barriers to green chemistry in the marketplace. I don't believe there are barriers to green chemistry in the marketplace if you have performance, if you have cost. The only time it becomes a problem is if you're missing one of those things. Now, if you're missing performance and you're missing cost, all the meetings, all of the discussions aren't going to solve the problem. Who's going to solve the problem? The person in the lab pouring the beakers and flasks, inventing it in the first place. At the end of the day, this is a technological problem. Yes, there's a huge amount of policy and other things going on, but if we don't have the chemists in the lab inventing things, where are we going to go? You know, people have all seen my graph of all the environmental regulations by the U.S. federal government and how there's an exponential increase in the 60s in environmental regulations. Industry recognizes that this is a major impediment to success in the marketplace. We're not having to convince people of this, but the problem is when they look at their workforce and they say, hey, workforce, you chemists and chemical engineers and material scientists that are inventing our next generation materials, make sure that you invent it in a rational way that prepares us for these environmental regulations. It's almost like, oh, I hated that in high school. The chemists are saying, I don't know this. This isn't part of who I am as a scientist. I get it, but I've never had a class in mechanistic toxicology. I never had a class in environmental mechanisms. Heck, I never had a class in law and policy. You're asking me to invent materials under a set of descriptors that I have no training to do. So stating the need, insisting on it, is part of the problem, but the solution is how do we get a workforce that's capable of doing it? If no one, there's still not one university or college in the United States that requires chemists to take a class in toxicology, environmental mechanisms. Think about it. Doctors, lawyers, teachers, nurses, architects, engineers all have licensure to practice their trade. They have to, on a regular basis, get continuing education to show that they're up to stuff with toxicity and safety and things like that. My father was an electrician. He couldn't come to your house and change a light bulb unless he had a document from the government saying he could do it safe. But we chemists can go in the lab and make a molecule that has never existed in the universe before, assembling atoms in unique geometries that God never intended, and potentially making, sorry about that, potentially making the most potent carcinogen in history, and nowhere in their training did they have to have any course to anticipate that. That's a problem. We need to change this. And so we've heard a couple times this discussion about this green chemistry commitment. Berkeley is in the front line of changing the chemistry curriculum, not just at Berkeley, but in the world. By leading by example, by getting into the curriculum and changing this thing, there's actually hope that we can do this. You know, usually when we face some kind of tragic problem, okay, when we face something as enormous as this, as toxicity in the environment, it impacts in the environment and in human health, it's so easy to spiral into despair and say, oh my God, this is terrible. I don't want to hear about it. I don't want to think about this. And we just really get upset and nervous and sad. But that doesn't solve the problem. Can you imagine, I always say this, can you imagine if Dr. Martin Luther King got up and said, I have a nightmare? I think he would have gotten funding. People fund nightmares. But I don't think people would have been activated to solve the problem. Positive paths to success, to solving a problem, is what activates people. And because we know that chemists aren't being trained in mechanistic toxicology and environmental mechanisms, we actually have a path to solve a problem. It's not like we don't know how to do this. Can you imagine if every chemist that's practicing in labs around the world actually did have the ability to recognize mechanisms of environmental and human toxicity? Can you imagine if the field of toxicology, amazing field where people are working tirelessly to develop understand new mechanisms of impacts and stuff like that, that's going on. There are journals being published, there are books being published, there are conferences being had, but the people who are pouring the beakers and flasks making molecules are completely unaware that they even exist. If we can create that conduit, if we can speak the same language, if we can collaborate in that way so that those developments are immediately ushered into the research and development labs, we can start solving these problems. And so here's the trick. By doing that, not only do you have safer materials that are non-toxic, but because no one is learning this, if you or an organization follows this approach, you're probably going to be more innovative, not less. You're going to be more creative, not less. And so one doesn't succeed in spite of green chemistry in a global competitive market. They succeed because of green chemistry in a globally competitive marketplace, because it is a differentiation of how all other scientists are working. Okay? I do believe that because of the Herculean effort here at Berkeley, there is a day in the future that I hope I live to see where every chemist does learn about green chemistry and mechanistic toxicology. There will be a day where we'll just look at this as, of course, this is part of who we are as scientists. But that's not going to happen tomorrow. It's going to happen in a decade, maybe longer. So the clock right now is ticking that those organizations, the universities, the industry laboratories, the government laboratories that embrace this, will be ahead of the pack. And before everyone is doing it, those who are first adopters will have the opportunity to define that future and to actually enjoy the benefits of being first to market with these technologies and to be able to doing this. But at the end of the day, that capability doesn't happen because we want it to. That capability doesn't happen because we make it very expensive not to do it. That capability doesn't happen unless we train the workforce inventing the molecules to understand how to do it. And so that's the opportunity that we have in front of us, is that by looking at the curriculum and understanding what the curriculum has in it. Obviously, we have a great curriculum. I mean, the field of chemistry has done amazing things in the last several decades. We can't fault it for not being, but just because something is excellent doesn't mean it can't be better. Okay, so this is not a condemnation of how we teach chemistry. We do a damn good job. It doesn't mean we couldn't do it better. Okay, and so that's what we really want to do here, is we need to look at, we can never sacrifice excellence. All right? So it doesn't mean let's take excellence out of chemistry and replace it with toxicological awareness and knowledge. I wouldn't say that. I honestly don't believe there's a such thing as a professional green chemist. Okay? There is no such thing as a green chemist. A green chemist is a half human, okay? A medicinal chemist who does green chemistry is an excellent medicinal chemist. A electronics scientist who does green chemistry is an excellent electronic scientist. Green chemistry modifies something else. It isn't an end upon itself. It's doing something else better. Okay? And so I would never suggest that a company or an organization hire a green chemist. They should hire an excellent scientist that also knows green chemistry. That's an important distinction. It isn't a profession upon itself, okay? It is a modifier of other professions. For those who are chemists in the audience, how many people had organic chemistry in the room? Oh, good. I won't kill everyone. All right, imagine, you remember E1, E2, SN1, SN2? You remember you learned that stuff in organic chemistry? Most people treat that like the measles. You have it, you get over it, and you never think about it ever again. All right, I would argue that you can be a very successful chemist and never think of SN1, SN2, E1, E2. You can solve problems, you can get pats on the head, get patents, be a very successful chemist, never thinking about that stuff. However, your best chemists are always thinking about that. They're understanding that mechanistic theory as they're designing chemistry. Can you do pollution prevention and non-toxic materials, never hearing of green chemistry or the principles? Of course you can. It isn't necessary to do it, but I would argue in the same way that mechanistic theory of reaction design helps a chemist perform that job, understanding the 12 principles of chemistry create an intellectual framework to enable that to happen better. It is not a necessary requirement, but it does help. Okay, and that's all it is. It's a very modest, egoless thing. It's not saying you must do green chemistry to accomplish these things, but it's the intellectual framework that helps. And if we don't have that intellectual framework, then what are people doing? How do we know that we're really doing the right things? And so that's really, when you get down to it, that is the importance of green chemistry, is how does science grow? How does science develop over the years? It develops through conferences like this. It develops through journals. It develops through textbooks. It develops through all kinds of ways that scientists communicate. And so the science of green chemistry is a place where people can talk about, hey, I made this reaction and I changed this solvent and it was pretty efficient and it was less toxic and it was less biodegradable, and it creates a forum for scientists to interchange ideas and exchange progress so that we can build on each other and get to a point where someday we've solved some pretty significant problems. But the mistake is to believe that we can do it tomorrow, that this is just a desire. We snap our fingers and chemical industry is now green. Good luck with that. It's going to the modern chemistry has taken 150 years to get to where it is. It's going to take 150 years to get to a truly sustainable future, hopefully a lot less. Because of the work that Berkeley's doing, leading the way, I think we're going to accelerate this thing and not have to wait 150 years. But it isn't going to happen overnight. We're going to have to accept that the enemy of the excellent is the perfect. Someone who invents a new way of reducing the toxicity of a product may not simultaneously make it more biodegradable. We can't vilify that for being imperfect. That is a great technical achievement. Someone else may come up with a way of making it more biodegradable, but hasn't addressed the energy issues. Well, we've got to celebrate that because that's part of the problem. Now, if we put these scientists together and build, then there is a future where these pieces come to play. That has to have that intellectual framework. That intellectual framework comes from academia, comes from classwork, comes from structuring bodies of thought to be able to enable these collective advances to be put together synergistically. That's the opportunity that we have, and that's why I'm just so optimistic that we can pull this off. All right, because the path is not obscure. The path is fairly clear. The desire is there. The problem is have you looked at the chemistry curriculum lately? Where are we going to fit this in the chemistry curriculum? All right? And the second thing, if someone does want to teach it, well, no one's ever had these classes. Who's going to teach the classes if they've never been offered before? Where is the curriculum going to come from? Now, although that's a problem, those are solvable problems. All right? We can find ways to fit it into the curriculum. It's not a one-size-fits-all. For one university, it might mean offering a separate class. Another university might want to integrate it into the labs. Another university might find a way of doing it. There's all different ways of approaching this. The trick is to make what works for each organization work for that organization. Seeing that it can be done is 99% of the problem. Okay? If someone says it can't be done, then they don't try. But when they can look over here to the West Coast and say, wow, look at what Berkeley's doing, maybe we can do it too. I couldn't be more optimistic. Thanks.
Thanks very much, John. Our next speaker is Dr. Michelle Dusky. Let's welcome her to the stage.
How are we doing? I think I'm on. Perfect. I'm on the desktop. Thanks. I retitled this opening slide for a different talk. Used to be called a Little Green Fish in a Big Pond, and hence the fish. But I just kept the fish, and then I reconfigured it for Blue and Gold Made Green. Go Bears and go Gophers as well. I'd like to acknowledge the Minnesota. Part of what I want to address today are changes that we've made in our curriculum and concerns that I have on going forward. The changes that we're making are very exciting. So we're introducing issues of sustainability into the curriculum. We're bringing in green chemistry, sustainable design into the curriculum. And I'll point out just a couple different examples from our general chemistry for majors class and our general chemistry for non-majors class. And then pose the challenges of thinking about what about the sustainability of the curriculum? There's, I think people that teach often see this happen. There's this big movement. There's a lot of changes. There's reform. And then stagnation for how many years? 10, 15? So I think that we need to push forward from a curriculum design standpoint to say we want to continually renew our curriculum, and we also want to sustain the changes that we do make. So I think that's kind of a twofold problem with some similar solutions. So Berkeley is a semi-big school. I was reminded by Professor Tolman that it's not as big as Minnesota, but we have more red tape, so we make up for that. And we have about 25,000 undergraduates, and over half go through the chem department. We're half. Little bit more females than males, and we have Oski Bear here to charge us forward. This is a snapshot of Pimentel Hall. So there was reference to the good old days. I think Wheeler Hall is the one that seats 800. Pimentel Hall, for those that haven't visited, is really fun because it has a rotating stage, so you can set up these elaborate demos and then just roll them, rotate the stage on, and surprise the children, which is, I shouldn't say children, the kids, the students. For the students in the audience, I apologize. Now, my job, so general chemistry, we see about 2,000 students in this class throughout the year. The fall is the biggest slump. The fall is the incoming freshmen and all the new graduate students. So my job in the fall is middle management. My job is trying to make the curriculum run smoothly, make sure the GSIs are well trained, and hopefully buy into the new changes that we're making and things like that. Chem 1 is a service course, and it has an accelerated curriculum due to some requests from the biology departments. The biology department said, our students are spending 2 years in chemistry before we can allow them to take Bio 1A, and couldn't you just slim that down? So we did. And Chem 1A is the only general chemistry class that many of the students on campus will take, and they go right from there to organic. So we have a very fast curriculum. We're trying to keep it meaningful and deep, but it is pretty accelerated. Now, I wanted to speak a little bit about the trajectory. It was a fateful conversation in November 2009 when John Arnold sat down in my office and said, what would you think about revamping the Chem 1A laboratory curriculum for green chemistry. And I think I readily agreed. And he said, what did you need? And I said, time and space and money. And by January 2010, he's like, we've got it. We got the grant. I was like, someone was writing a grant? So I was in the enviable position of just being part of a team, not having to have done any of the front-end labor. And I realized soon that I would be doing all the back-end labor. But we were funded by the California EPA Department of Toxic Substances. Thank you so much for that. We had some seed money that funded us for 2 years of development. And together with my colleague Barney Mulvihill and some inspiration from the University of Oregon Green Chemistry Education Workshop Series, I was quickly brought up to speed and started helping to develop new labs. And we did something that I would never ordinarily do, and that was develop new labs over the summer and launch them in the fall for 1,400 students. So I crossed my fingers, I pulled my hair out, and I hope for the best. People that know me will call me a micromanager. People that know me better say I'm a micromagicer. I like everything buttoned down in Chem 1A. I like everything to run smoothly so that the GSIs can focus on their teaching, so that the students can focus on their learning, and they're not encumbered by just the enormity of the course. And so launching 6 new experiments was challenging. I learned it was doable, and we had wrinkles. People rolled with it, and we're talking about the students rolling with the wrinkles that we had and the GSIs because they believed in the green chemistry message, and they were excited to be a part of the testing team instead of frustrated to be a part of the testing team. Our approach initially was to just look at the laboratory curriculum that existed, identify what the goals were, and try to come up with greener context, greener solutions, and above all, be communicating the fact to the faculty that the rigor was not lost, and in fact the rigor was often enhanced by the new program. But as happens often, if you think about changing things, people get nervous, and so we have to make everyone happy as much as we can. Now, one of the first experiments that we worked on to go into the unit of thermodynamics was a biofuels unit, and this was something that Marty took the lead on. The students do a 3-week set of experiments that are all related to biofuels, and then they can actually draw conclusions at the end of this module where they've really been steeped in this context. They can draw meaningful conclusions. So the first week they do a toxicity assay. So up in the corner here, if there's a laser pointer, there's a diagram where the students made cereal dilutions. They put radish seeds in little petri dishes under varying conditions of biofuels, varying concentrations of biofuels and regular fuels. Put that into their lab locker, came back a week later and opened up these little salads that had grown or not grown in some cases, and they got a little glimpse at ecotoxicity by doing this simple assay. Second week of lab, they made biodiesel and they burned biodiesel. So what we kept was a calorimetry lab that is so important for a general chemistry curriculum. Students need to understand about heat transfer. They need to know how to measure heat transfer. But we provided now a context of something that they're actually excited about. They were so excited that they made biodiesel and they burnt it the next week. It was their fuel that they made. And many of them probably the first time they've tried to germinate seeds, depending, and so that was an exciting thing as well. So definitely we saw that we were maintaining rigor and we were enhancing the experience for the students. So by the end of it, we could ask them questions about comparing the biofuel they made to, say, ethanol, writing a short paper on that, and they're bringing in all these outside topics, all these outside readings, in addition to doing that whole page of calorimetry calculations. So they were connecting their science to the world around them, finally, and it was really exciting. I have a love of assessment, and I always want to know what are the students taking away from this process. So we're just beginning some preliminary work on trying to figure out what the students are getting. The early assessment indicated that they do agree that green chemistry techniques are important. They don't agree as much that it might be important to their major. So most of the majors in this class are bio majors. But for the most part, they're buying in. So I wanted to think about what are their attitudes towards green chemistry, but I also wanted to think, well, what are you thinking about in terms of the energy industry right now? Just like an intellectual question. So I gave them these two reactions. The first is combustion of coal, and the second is the combustion of methane, which they may never have seen before, depending on their level of experience. And I asked them, they're both used to generate, they could be used to generate energy in a power plant. Which one would you choose and why? And so these are just a couple of their responses. And it's interesting, it reveals some of their misconceptions about chemistry in general, but it also reveals what factors they're already zeroing in on that are important in terms of energy consumption. So some people are dwelling on which one is going to give you the most energy, just as in general. And some people are thinking about, some people knew this was coal, or maybe they looked it up. They're thinking about the unwanted side products. Sometimes there's comments about carbon dioxide and the NOx and SOx given off. Green chemistry is a new phrase for many students, so we wanted to see what were they thinking about this so far. And a lot of them are thinking about it from a regulatory standpoint or just identifying hazards. But a few people are starting to think about it as a minimizing hazards. So I can imagine building out this assessment piece would be getting their initial impressions on some of the science and their attitudes about green chemistry and seeing how that changes through time. Because we have decent measures about how their chemistry grows, but I want to know how their more holistic ideas are growing as well. Then we turned our attention, we're still working on Chem 1, but we're turning our attention a little bit to the majors Gen Chem class, which is the Chem 4 class. Much smaller class, a little bit easier to manage, only about 200 students in one lecture section. And they get a 4A and a 4B, so they get a full year of general chemistry and quantitative analysis, and they can go pretty deep into all these topics. And a highlight of the course is this student laboratory research project. So our students are steeped in this right now. We're going to have our poster session on Saturday. But the research topic is their chance to ask their own questions and execute it, and many of them do choose green chemistry applications there. So we've been working on Chem 4 experiments to build nanoparticles with less hazardous substances so that we can motivate the quantum mechanics section of the course. Silver nanoparticles are showing some promise because they have antibacterial properties. So it'd be kind of nice, I think, to make a nanoparticle, characterize it, you get your spectroscopy there, and then what are you going to do with it? You're just going to be excited because I made a nanoparticle? No, I'm going to kill some bacteria with it. What are we doing with these particles? I think that's important. So we're working on that. That's tough chemistry. I've been fascinated with extractions as well and looking at natural products that have some interesting properties. So we've been working on the limonene extraction from orange peel, and then also the new one is thymol from thyme leaves. I think there are people from Method here. Is that correct? Anybody? Yay! So green cleanser. Turns out you can use thyme to clean your toilet. Who knew? I knew. It turns out I knew, and I had an epiphany when I was cleaning my toilet that, oh my God, I could write the best HPLC lab about this. So my Minnesota analytical chem roots are showing there. The limonene lab we did build out, and Heather Buckley has a poster on that outside. So there is a known way to extract, do extractions. The go-to method for years and years and years was like methylene chloride will extract anything out of anything else. Let's use that. And then when we do that extraction, we can use more methylene chloride in our analytical technique of choice, and that'll be great, and we'll get lots of yield. So we substituted out the methylene chloride in the first step and did the liquid CO2 extraction. Anybody that's done this knows it's a good time. You put the ground up orange peel in a falcon tube and put in a bunch of crushed dry ice, put the lid on, and put that in a warm water bath, preferably in a column so that it'll, if the lid does blow, which it usually doesn't, it will blow more toward the ceiling. And it's really fun. Many of you probably have not even seen liquid CO2 in real life, and the students are seeing this percolating out, and limonene's a liquid, and it collects in the bottom of this tube, and it's very gratifying. The whole thing is just really gratifying. So we had to kind of stop ourselves, we even have this written in the procedure that we're going to do an internal standard, we're going to do gas chromatography, we're going to do external standards, we're going to have them compare and contrast. Students are going to dilute their sample because it's too concentrated. They're going to put that in methylene chloride, and they're going to zip that into the GC. And I just caught myself thinking, I know that methylene chloride is absolutely always what I use when I go and do gas chromatography, but why are we doing this? So I had to even catch myself, even though I've been steeped in this. And we substituted ethyl acetate. It worked great. It eluted before, the solvent eluted before the limonene came out, and we saved all that halogenated waste for our students. And many of them are making substitutions like this in their own special projects that they're working on. So again, I encourage you to go see Heather's poster. This is a snapshot of Heather in the wild, I guess, in her gear. If you want to see more details about this, we do hope to submit to JChemEd. It's not rocket science, but it's greener analytical, which sometimes isn't done, which is exciting. So our key factors in the success. We have been given money and space and time. Time is mostly during the summer session, but some new funding is freed up, some of us up for during the school year as well. We have the right team of people on board. So Marty kicked off a lot of this. I came on board. Now we're bringing my colleagues Ann Berenger and Marianne Roback on board as well for lab development. So we're building out our team of people. We've had students that have volunteered our time. We did not pay them, and they came anyway. Tons of students to help us develop labs. So it's just been really great and really energizing. Our money, initial funding, like I said, came from the Department of Toxic Substances, and that was key to getting this project off the ground. And with that money, we developed something like a dozen lab experiments. So we covered a lot of ground there. And then I also wanted to point out that the department was on board with this. So besides the fact that my colleague John Arnold was on board and the other people that were teaching the general chemistry, we got buy-in from the dean. So it started to become a major fundraising initiative for our department. And it led to securing a big grant from the Dow Foundation for us. The grant is being put toward renovating the teaching labs. For those of you that have been to Berkeley in the past, the teaching labs do look exactly like when you were there, and your initials might yet be carved in the in the lab bench. I mean, they haven't been renovated since they were built. So we're working on renovating them now. We've got 2 labs done. We're overhauling the storerooms, and we're building out, my favorite, the instrumentation facility. So our students are really going to use HPLC in their freshman year, and their sophomore year, and their junior year, and their senior year, finally. So thanks to the dean for that and the Dow Foundation. But the EPA piece was a key thing because that was a proof of concept. We have a model for churning out these new experiments and thinking about the curriculum. Now our challenges now, I don't always teach Chem 1A. I don't always micromanage it. And when I'm not involved, sometimes the faculty that are teaching say, oh, no, I just want to do the old labs we used to do. So we've developed new experiments that have not yet been taught all year round, and that's a frustration. So if we can get some more support and get more people that can help shepherd the program to keep it sustainable, that would be great. Of course, I would love administrative support for people to help me move paperwork, submit grants, and things like that, and more time to think, because we've been doing things a little bit piecemeal, and I want to think of it more holistically, as John was saying, to think about folding it into the curriculum more fluidly. And in future work, we're just going to continue to try to build out a suite of experiments, hopefully in these modules of 3 that could be taken and chopped up, but built out with the intent of providing a broader range of experience on a specific context, like we did for the Biofuels Lab. And I want to push on this assessment piece because I think it's important to try to figure out if the changes we're making have a positive impact on the students. And I believe they do, and I can see that they have a gleam in their eye now, but we need to track it. We need to get some data. So how do you define these new criteria for what you want to measure? It's a whole different measuring system. And I wanted to thank our funders, Kelley, PA, Department of Toxic Substances, the Dow Foundation, The chemistry storerooms were incredibly flexible and footed the bill for a lot of things that we needed. The publisher of our lab manual just said, I can't give you more time to publish the lab manual, but I can give you a few $1,000s to help you ease your way. And I was like, that's fine. I'll take whatever you've got. Our dean had chipped in some money. And then the folks at University of Oregon did a lot of training for us. And I'd like to thank my colleagues at Cal, both new and old, Marty, John, Angie, Bob Bergman, Ann, and Marianne, and of course the Berkeley Center for Green Chemistry. Thanks.
Thanks, Michelle. That was terrific. Thank you. Last up before we have the panel discussion, we have Bill Tolman from University of Minnesota. So please welcome Bill to the stage also. Thank you.
Okay, thank you very much, John. And this is a tough act to follow. First, we had God. But actually, I didn't think of John as God. I thought of him more as an evangelist. So I have the evangelist, and then we had a wonderful graduate of the University of Minnesota, which is always a tough act to follow. So with that, let me begin and tell you a little bit about what we've been doing. It's interesting to hear the timeline that Michelle talked about. Actually, I think what we've been doing in Minnesota has been pretty much in parallel in terms of time with what's been going on at Berkeley. And we've been operating pretty much independently, which is kind of stupid in retrospect. But we should talk more, John, about what we're doing, what we're planning on doing, because I think there's a lot of commonality between the approaches we're taking to address the concerns that John put forward about education and green chemistry, and some things that we're approaching slightly differently. And I think that's good for discussion. For us, the approach that we have taken is to tackle the problem of green chemistry education in terms of our targets, who it is that we want to try to educate. And we have targeted our undergraduates through courses, our graduate students and postdocs primarily through research and not courses. That's been our decision. We've also focused a lot on public education, and that addresses a concern that John brought up before about this attitude towards chemistry, and that's something that we've actually worked really hard on, is public outreach and public interactions. And then finally, let me add in one more thing that addresses something that Michelle talked about, and that is getting buy-in from your faculty. And so this, as a department chair, this is always a problem that I have, is convincing my faculty to buy into some idea that I have. And they often are skeptical and too busy and whatever. And the problem is only a few faculty in my department are really outwardly interested in green chemistry education. And the trick is, how can we educate the faculty so that they can pick up the mantle more generally and start integrating and doing more of that themselves? So the question is, how do you get to all these targets? And let me just tell you briefly how we've tried to do that. One is laboratory development. Like Michelle, she talked about laboratory development at the general chemistry level. Our focus has instead been in the organic chemistry laboratories. We've also implemented a new course called Green Chemistry. That's for our majors, junior and seniors, and we've taught that for 2 years now. I've co-taught it with my colleague Mark Hillmeyer, a polymer chemist. And we're just finishing the second semester of teaching this, and I will be handing it off to a new faculty member to teach next year. So that's the beginning of the education of my faculty. Basically, other faculty are going to teach this course. And that's how you teach faculty, I believe, is you make them teach. And so someone else is going to be teaching this course, and they're excited and enthusiastic to do it, and they will take the mantle for a couple years, and we'll just rotate this around through the faculty. It may take a while. We've got 35 faculty, but we're going to get everybody involved, and everyone will have taught the course, I hope, someday. We also do it through graduate education and research, and also outreach and public policy, and let me touch on all those things. We've decided in our department to take a dual approach because I think there's two ways we want to approach it. One is that, as we've heard, green chemistry is a way of thinking, so you really need to just infuse it in everything, right? You need to implement it and integrate it and seamlessly into everything you do. But it's also really, what we've heard today so far, it's really complicated, and there's a lot of difficult ethical issues and very in-depth concepts and ideas that really need some focused attention. And so that's for that reason as well, we've decided that we want to also explicitly teach it in a course to undergraduates so that we spend a whole semester actually delving into some of these more gnarly issues And so we decided to do both things. So the first thing we've done is green chemistry in the undergraduate curriculum. We are a big university. I think we have 38,000 undergraduates out of about 12,000 graduate students. So we're about 10,000 more undergraduates. And we have about 11,000 registrations in our chemistry courses per year. So we have a lot of students that go through our program. We focused primarily on our undergraduate organic laboratory course. It's for sophomores. It's about 1,000 students per year take just this one organic course, with about 120 majors integrated into that particular course. Jane Wissinger is the one who runs that. She's a faculty member in the department, is a term faculty member. This is a 2-semester in one course. So we teach the organic lab in 1 semester. So it's a 4-credit course. So that's why there's that boot camp picture. It's pretty intense. It's 8 hours of lab per week. So it's 2 afternoons of lab. So it's a pretty heavy-duty course taught by 35 graduate teaching assistants. And there's about 18 students per TA in the lab at any one time teaching this course. And basically, I don't want to go through all of this. Focus on the blue here. Basically, since 2002, we've been trying to push little bits and pieces of green chemistry into the laboratory. We faced the similar problems that Michelle did, time and money to do this sort of thing. And so Jane has really taken the lead. She attended the green chemistry workshop in Oregon. And then she, in 2009 to 2011, she developed a new experiment and published it. And then in this last year and this year, there's 2 more new experiments going in. She did get a small grant from the Minnesota Pollution Control Agency for integrating some sustainable polymer synthesis into the laboratory. So it sounds a lot like what Michelle is doing, slightly different in that it's organic, not Gen Chem, but it's a very similar type of approach in reality. Here's an example of one type of progression of how this has happened. This was the way that we used to do this experiment. This is the standard textbook, sodium dichromate oxidation of an alcohol to a ketone. Clearly, this is bad. And so we made it better. So we just used household bleach, and this was great for a while, but not so great. There were a lot of unreliable results between sections, and there was wet products, so there were yield issues. There were some noxious fumes that we had to have hoods for, and hoods are expensive, and we're running out of hoods, and that's an infrastructure problem that we're facing. And there were all sorts of mixed messages on bleach and non-chlorine bleach that we were sending to the students. And so more recently, Jane has actually just turned to the oxone and using sodium chloride as the catalyst. And so with a little sodium chloride and some oxone, it's a much better experiment. It's much higher conversion. It's much more reliable. And it's much greener. And so this is the sort of evolution that has gone on over many years in sort of greening experiments as we go along in the undergraduate laboratories. And that's just one example. We've also done assessment, and the students do love it. They really value it. They think it's great to do this procedure. In this particular procedure, the fact that the product's actually used in a research program in the department, so the product is actually used, they really like. So it's not just thrown away. They're actually using it for something. So the students really dig it. And one of the things that we see, I'm going to talk next about the course in green chemistry that we teach a little bit later. The students coming into that class have already taken this lab, and they come in already loving green chemistry. It's amazing. The students really do jump all over this. So this course, I think, does all the sorts of things that you want it to do. It educates a lot of undergraduates in green chemistry at a relatively low level. I would like to see us get more green chemistry into our general chemistry laboratories, and that's something that's on the docket for us. And how we're going to integrate that is going to be interesting, because I think we're running our labs a little differently than I do here at Berkeley. We're running them in teams of 4 using the process-oriented guided inquiry approaches to solving labs. So we're going to have to figure out some ways of doing this, and I'm going to work with Michelle, and she's going to help us figure this out. She has free time. Our new course in green chemistry, I've taught that with Mark Hillmeyer for 2 years now, is a blast. A really hard course for me as a faculty member. I had a lot to learn to teach this course. But here's some examples of the things that we've done. We start the course talking about Rachel Carson and DDT and the whole controversy over DDT. We talk about the public media and the origins of modern environmentalism. We've also, this year, read some chapters from this great book by Sean Lawrence Otto. I hope you've read this book called Fool Me Twice, Fighting the Assault on Science in America. He's a Minnesota product, actually went to McAllister. And then we talk about waste prevention, remediation. We talk about catalysis. We talk about environmental performance. There's a lot of readings. We talk about ionic liquids, renewable resources, chemicals from biomass, and ethics from biofuels. And we do a lot of case studies. And so here's some examples of case studies. I mean, there are many, many other case studies one could pick. And these are the ones that we happen to be doing right now. One of them is a little odd. I'll point out this one right here, the presentation to Senator Al Franken. So it turns out that Mark was scheduled to go to a meeting with Senator Franken, and he was supposed to give a 3-minute blurb about what's exciting and important about green chemistry to the senator. And he came to the class and said, I have to give this 3-minute bullet talk to the senator. Help me. And so we turned it into a giant class project where the whole class had to come up with elevator talks about why green chemistry is important and how would you express it to someone who knows nothing about it and who's a comedian at the same time, and to be funny. So it was a real challenge. And they did it. They came up with a wonderful blurb, and Mark, sort of adapted it and did it. And Al Franken has actually come back several times to the department because he really enjoyed it and is really a big proponent of actually green chemistry legislation at the national level. We like to think in large part because we've told him to be so. Okay, that's not really true. But anyway, we also talked about the ethics of biofuels, and we analyzed articles in green chemistry. So it's been a really fun course, and it's not taught to that many students, excuse me. And it's 35 to 40 students. It's sort of an upper-level majors course, run like a seminar. We run it in our new Science Teaching and Student Services building, which has these circular tables with lots of high-tech stuff to facilitate conversation and interaction. So there's not much lecturing. It's mostly discussion in the class. So I would like to see the impact larger. I think we need to be more ambitious about getting this impact larger. The other thing I will mention, what makes this course really tick, there are topics, let me skip this. What makes this course really tick is we bring in a lot of guests from people from the outside, and I know that's something that Berkeley does as well by integrating people from different departments into their curriculum. I think that's a great idea. We bring in people from local companies, 3M, Sagetis, NatureWorks. We had a great talk this year by Steve Hecht, who's an outstanding toxicologist. He came in and talked about cancer toxicology, and that was tremendous. Deborah Swackhammer is really a leader in the country in public policy about water resources. Water is a big deal in Minnesota. We have a lot of it. And we also had somebody from Aveda come in and talk about in products like that. So this sort of stuff has been great. And finally, the person at the top, Steve Kelley, he was a senator for 10 years in our state legislature. And he's our director of the Center for Science, Technology, and Public Policy at our Humphrey School of Public Affairs. And he came in and talked about public policy and what it means and how to go about it. And he's been a really important player in green chemistry development at the university. The other part of what we do is was stimulated by a picture like this. I don't know if you've ever seen this. It's a really beautiful artistic picture. If you zoom in on this picture, you'll notice, however, what it is. It's plastic bags. And it represents the 60,000 plastic bags used in the United States every 5 seconds. And it's a beautiful website. I would recommend you go there to see the other art, environmental art. And this stimulated us to ask the question, what can we do to replace that plastic? And the problem is we need plastic. In a world of 7 billion souls and counting, we are not going to feed, clothe, and house ourselves solely from wood, ore, and stone. We need plastics. The trick, of course, is to make them sustainable, to make them from renewable resources and biodegradable, and do this in an economically cost-effective way, and moreover, to come up with plastics that have better performance properties than the ones that are already out there. And that has led us to the new Center for Sustainable Polymers, which is directed by my colleague Mark Hillmeyer. It was established in 2009 with seed funding from a local source, Initiative for Renewable Energy and the Environment. And we were awarded a Phase 1 Center for Chemical Innovation grant from the NSF just this last September. And now we're on the hunt for Phase 2, which is the real money. And so we're really excited about this. Right now there's about 39 students, postdocs, and other participants. And this center includes people from multiple departments: chemical engineering, material science, that's CMS, chemistry, bio-based engineering, and also Steve Kelley from the Humphrey School. And also Jeff Coates from Cornell, and we're going to be expanding to other scientists from throughout. This center is a research center. Okay, so the focus of this is research, and we have a mission and a vision, and for the sake of time, so we can have more time for discussion, I won't read all of this, but there's lots of buzzwords there. Basically, what we're trying to do is innovate. We want to innovate. We want to discover the fundamental chemistry that's required to design new types of sustainable polymers and get them to the marketplace. So true innovation is our objective. To make this happen, a key is partnerships with companies. So there are now more than 20 company affiliates associated with our center. Most of them have given money to us and are actively involved in participating in our center activities. And you'll recognize a lot of names here. All of these companies are really interested in sustainable polymers. And we're excited about the opportunities by partnering with companies like this and actually bringing our stuff to market. The most important thing in the context of today's discussion is this is a way, I think, of teaching graduate students and postdocs about green chemistry, getting them involved in research at the forefront of sustainable research. And that's one of the key objectives of this center, of course, is to educate those folks. One of the other things that we really spend a lot of time and energy on is outreach as well as doing research. And here's a photograph from something really important that we do, and we've done for several years now. We have a big booth at what's called the Eco Experience at the Minnesota State Fair. If you've ever had a chance to go to a Minnesota State Fair, I highly recommend it. It is a hoot. It's an amazing place. There's an entire huge building filled with stuff like this. And more than 300,000 people go through this building in a 10-day period. We staff this thing for the entire time of the fair with people from our center and from the Department of Chemistry. And we show people, you can see molecules in the front, and we teach people about sustainable polymers. And we engage in all sorts of public conversations with the public here. And it's really fascinating to see the way people come in and how they learn about what we're doing. It's a great outreach opportunity. We also, this past year, we did a show for 10,000 middle schoolers. We had them in for 3 shows a day for 5 days, 350 kids per show, called Energy and You. It's a show where we blow up stuff and teach kids about energy. And all the kids learn one message, and the message is simple. Energy. You can't make it, you can't destroy it. That's it. They walk out, they know that. Okay? They know a few other things, but that's what they really know. And sustainability concepts in green chemistry play a big role in this show. And Mark Hillmeyer and other participants in the center are part of this show. And so we really take this public outreach thing really seriously, and we're really impacting a lot of people in this way. And I think this is something that's really important for the future. Finally, this year, Steve Kelley is going to be running a public policy roundtable that's going to involve a lot of legislators from our state government who are going to come and meet with us and talk about green chemistry and bio-based materials and sustainable technologies as a way of bringing public policy into the picture. And most importantly, our students who are involved in the center will be participating in this public policy roundtable. So we're going to have a direct interaction between the students and the legislators. And I think that's also a really important part of anything that we do here. So with that, I will finish and just say, I think there's a lot of different ways of doing this. Green chemistry education is obviously really important. And I think that we at Minnesota and here at Berkeley are taking complementary approaches to the whole thing. And I think you'll see at other schools different approaches as well. And John pointed this out, that it's all good, I think. But I think one of the challenges that we have going forward is we need to communicate a little bit better with each other and work together to implement things that work and warn people off of things that don't work. And that's something that I think we can do better at going down into the future. Okay, with that, I'll finish. Thank you very much.
Thank you. So I'll invite our other 2 participants to come up and take a seat on stage here so we can start the discussion. So we'll open the floor up to questions shortly. But I had a couple of things to ask first. So we talked a lot about sustaining the sustainability here, and if you make changes in your curriculum, how are you going to make sure that in 10 years' time you can still do that? This bears on questions relating to academic freedom. So I have colleagues here at Berkeley who, if I walk in and say, I've got this great idea, we should teach green chemistry, you should teach this in your lecture course. Some of them will be amenable to that, and some of them, let's say, will be less amenable than others to doing that. We've taken the tack here initially that the best approach for us is to tackle laboratory courses first, and I think there's two reasons for that. One, I still believe chemistry is an experimental science, and I think you learn it best by doing it, and I think many undergraduates get turned on to chemistry when they have a good experience in the lab. So I think we should do as good a job as we can in the laboratories. And I think things are changing here at Berkeley for the better because of the developments that we're going to make in Chem 1 and Chem 4 that we've talked about. I think a lot of the credit for that change has to go to our administration and Dean Richard Matthews, who's been the first dean to really push this through and make sure that this happens. The second thing is we have more control over the laboratories, over what goes on in those laboratories. And if you make a big change, particularly in a course that's dealing with 1,500 or so or 1,400 students per semester, it's a lot harder to change it back to something else. So that's the tack I think that we've taken. But Bill, at Minnesota, you have a course in green chemistry. Not everybody's clearly taking that course. What else do you think you can do in terms of the lecture courses and that material? What can you do right now versus long term? So I see this change as happening over a very long term. It's a generational change. As students get educated and as they go through the labs and as they go on to be postdocs and professors and leaders in industry, they will bring in change to the jobs that they do down the road. But is there anything, particularly as head of department, that you can do right now that will change how you teach freshman chemistry lecture, for example?
No, I can't do a damn thing. No, it's a good question, and I think it's a challenging one. I agree that the labs are a really important part of it, and I would like to see us incorporate more green chemistry into our Gen Chem labs to get even more spread. I think that's really critical. I view the class that we have now as sort of an advanced level for the aficionados type class. Okay, so that's not meant for everybody. That's meant for a cadre of people who are particularly interested and are willing to spend.
They will go on.
Yeah, and they will go on
great things and hopefully take that.
Exactly. But to integrate actual green chemistry into lectures and general chemistry and so on, I think that really depends on the key resource. And the key resource is people like Michelle, or people in my department like Michelle Dreesen or Jane Wissinger, who are faculty members who have taken on the responsibility. And they're, both of them in our department, so our director of general chemistry is a big fan and is interested in doing this. So she's been focusing on the Pogul stuff for now. Once we get that taken care of, the green's going to start seeping. You're right, it takes a while. In terms of permanence of sustainability, at the end of the day, isn't it just leadership? I mean, it seems to me you've got to have the faculty at the top of it championing it all the time. Mm. And I think that's really
also,
important.
In chemical terms, delta G has to be negative. Mm-hmm. It has to be viewed as something that can happen, that this is a good thing to happen. We have a barrier to get over, and we have catalysis to get us over that barrier.
And you and I know that the trick here is we need to tout what we're doing. We need to be evangelists like John. So I look at John, I say, oh, he's such a great evangelist, and that's something that we're working both of us independently are working on this really hard. We tout what we're doing. We do a lot of media stuff. Our latest issue of our department newsletter, which you got, had a big 2 articles about green chemistry in it. And, we have to make it into a big thing and keep it on the forefront and keep pushing it. And I think that's really important. We heard about from Move On how important this sort of networking stuff is. And we have to play that game as chemists. We have to play the social change game. Mm.
And I think we have an audience that's very receptive. That's certainly been true at Berkeley. It sounds like it's true at Minnesota as well. Marty's the sort of poster child for that statement here. Marty is a big reason that we're all here today.
Yeah.
He played
He's
a huge role.
John. He's the catalyst.
He's the catalyst. And getting together with people in public health, as Marty did a few years ago with Mike and Meg, and the Berkeley Institute for the Environment roundtables, and all of that. It's taken a while to get us to this point. But it is a sort of bottom-up led movement, and students really want this, which is why I think Delta G is very negative here, and it will happen. Our job is to speed it up a little bit. So one last question from me. Particularly in freshman chemistry and in lecture courses, not necessarily just in freshman chemistry, but freshman chemistry I can see as a big place for change here. You need a textbook for most of these things. And I was wondering if the panel or anybody from the audience had opinions about the textbooks that are out there right now, if there's a particularly good one. And by a good one, my definition of that is that the science in there is first rate, but that the science in there is illustrated throughout that book using principles of green chemistry, as opposed to either no mention of green chemistry, which is true of most textbooks, or in some textbooks now there are sidebars that mention green chemistry, or there's a chapter way at the back that you'll never get to that has a chapter on green chemistry. So how important is that? How important is an integrated textbook that does the sort of stuff that we're talking about? And then the last part of my question is, many people have already mentioned Oregon here. Oregon, organic chemistry has played a big role in development of green chemistry. Many of the people in the audience have been to their summer schools for organic chemistry. Is there a place for doing that at the freshman level?
Well, I'll start by saying, we need all kinds of curriculum. Every university, every faculty member has different needs. I don't know that we're looking for this magic book that fits for everybody, because there's different needs. But we do need to have that curriculum, because I think it's a two-step process. One step is obviously, getting the faculty to want to teach it. And then once they say, I want to teach it, giving them curriculum to teach, and so it's a two-step process, and we need not to overthink what the perfect solution is, but to have a diversity of solutions so that we can mix and match and make it work whatever way. So anyone who is interested in creating high-quality curriculum should do it right away, and not worry about the enemy of the excellent being the perfect. Get anything out there. There's the GEMS database that's being run by University of Oregon. Berkeley is creating its database. The American Chemical Society's Green Chemistry Institute has a bunch of information. Getting the curriculum out there is critical in whatever form that we can possibly do it. Yeah.
Michelle, any comments?
Just that, yes, I need something. I guess what I struggle with is wanting to do more, but not having the time to learn. The learning curve is steep, and so I've been putting things in a little bit piecemeal, little modules, little homework assignments, and things like that. So the more that can be written and shared with others, I think would be helpful. And we've moved away in our curriculum, at least for John and Angie Stacy and March and Maida that's teach Chem 1A, we've moved away from requiring a textbook at all, and think of the textbook as a resource that is more like an encyclopedia. It's too exhaustive to really teach out of, so the students should be referring to it when something that we cover in lecture or in our additional assignments, and we have many of them, it's something to be referred to. And so although having one that matched our needs better would be great, I think you brought up an excellent point that everybody's needs are different.
I agree. I also think we really do need more textbooks that integrate it more effectively. Most organic textbooks, not all, but most organic textbooks in heavy use today in the United States still use lots of crummy reagents and lots of crummy processes, and they haven't gone even though they keep being revised and going through new editions so they can sell more and more expensive books and make more and more money, sorry, I'm a little cynical, they have not.
How is your former advisor, by the way?
What's that?
How is your former advisor, by the way?
Well, sorry.
He's driving a Ferrari.
He is, in fact, driving a nice car.
It's also a very good textbook.
It's a very good textbook, but I challenge you to go in that textbook, and I'm certain it could be much greener. So I think, but it's like everything else. You know, it's going to take some time, and I think it's really important. Even if you don't require the textbook as part of the course, and you treat it as a resource, the textbooks have to start reflecting this more and more, and getting it more or less sidebar-ish and more integrated. And the sidebar-ish stuff has got to end. Gen Chem text was the same way. They treat environmental chemistry all over the place. There's environmental this and environmental that and all the little boxes and pictures all the way around. But why? Shouldn't it just be in throughout and just be part of it? And it isn't, and I think that's the trick. So in my spare time, I'll just write a book.
We can collaborate in our free time.
Okay, fine.
I think there's money to be made there.
Yeah.
Yes. Questions? Let's open it up a little bit. So please say your name.
Mike Biddle. I'm president and founder of a company called MBA Polymers, started right here in Berkeley. We recycle plastics from end-of-life computers, electronics, automobiles, all over the world. Two quick questions. One, I love John's comments about a green chemist is only half a person. I think beyond just spreading the notion throughout the technical world, we need to spread this through the business world too. As an engineer that's now trying to run a sustainable business, it really gets lost in the business world. It's getting better, but we need to spread these ideas to the business world. So I'd like some of your thoughts on how you communicate that to your colleagues in the business schools too. And secondly, I like that you're using experimentation and examples because I think that's how people learn. At least that's how I learn. Let's see, I'm sorry. It's, Bill, you gave the example of sustainable polymers, something I care about. And you defined sustainability, I believe you said biodegradability was an important aspect of that. I would just like to, I think you would agree that growing, even creating a polymer from plant-based foods requires a lot of resources and energy, water, fertilizer. You have to harvest the crops. You have to then extract the chemicals and synthesize them still. So that's a lot of energy that's been embedded to make that polymer. I would challenge the notion that it's sustainable if it then degrades and it's a single use. I would think a better use of that biopolymer would be a recoverable. And I think even NatureWorks, one of your sponsors, has caught on to that and is now trying to promote recyclability instead of biodegradability. I'd just like to hear your thoughts on that.
Oh, I totally agree. I mean, there's many different approaches and many different kinds of sustainable polymers that we're focusing on our center. We're focusing on feedstock development. We're focusing on new materials with new properties. We're focusing on biodegradation is only just a tiny part of what we're working on. And it's absolutely true that some of the materials we make, reuse is more important than others. I don't think there's a single answer to the question. I think you're absolutely right. Sometimes it might be better to have it be reused, other times not. And it depends on the use and the particular application and the particular thing you're working on. So absolutely.
I'm just concerned if you're teaching kids that disintegrating, a material disintegrating at end of life is a good use, is maybe the best use. I'm just concerned. I don't think that's consistent with the bigger thinking of green chemistry.
Well, we can talk about that. I mean, sometimes it is. I mean, I think it depends. In some cases, I think it might make more sense to have it be. There are a lot of single-use items out there, and you're not going to stop them from being used in a single way. You're better off making them degradable. Is it perfect? No, I'm not. If there's not another way, if you can recycle. Well, the problem with recycling these days is what's the percentage of plastics that are recycled? I mean, it's tiny. 3%, 5%, I don't even know. It's tiny. So, yeah, I don't want to make the perfect enemy the good or the excellent, and I think that. But you're right. We need to address both sides of that coin. Yeah.
Can I just put a plug that you guys talk because we're trying to develop a polymer. Marianne, raise your hand. We're trying to develop a polymer module that involves maybe a recycling component.
I think there was a question.
Hi, I'm Bridget Luther. I run the Cradle to Cradle Products Innovation Institute, and the innovation part of Cradle to Cradle gets really interesting and starts to dovetail really quickly with the alternatives analysis and conversations that I've had with John. He's basically said, look, everybody's going to do these alternative analysis, and then we're not going to have the material that's a safe, healthy replacement for what they're trying to do with the properties that everybody wants. And I wish that around green chemistry would start to really do more visionary thinking about a materials revolution and what that would look like and how fun that would be if all of a sudden there was a prize or a grant or something that went to universities, and then these kids could say, oh, I've got to develop glue that can actually be really strong, that doesn't actually kill people and planet, and there you're in the lab and you're actually using the principles and not having to, it kind of gets to what all you're talking about. I think it also starts to elevate the conversation beyond green chemistry and makes it a little more exciting if you sort of talk about that. And I just like to hear what you guys would think about maybe that bigger vision about a materials revolution.
I think that I would like to incorporate, especially for the majors class, the notion of chemists as the molecular designers. You know, the Lyman and extraction lab is exciting and fun in its way, but it's just, you know, it's just an extraction and a quantitation, and it's, you know, nobody's really going to, as a chemist, well, I shouldn't say that. They're probably using it quite a bit, but let me not go there. But I'm pretty excited about some of the stuff that's happened in the Green Chemistry Challenge Awards, and there's some interesting innovations that I think we could build out as a teaching tool to illustrate how the chemists made a change and made a new catalyst that was friendlier than the old ones and made to degrade when they outlived their usefulness. There's some cool stuff there, and after we build some of that into the earlier curriculum, then they could accept a challenge like you're saying, where the students themselves have a bit of skills under their belt to just dig in. And I'm spoiled to be at Berkeley. The Berkeley students are really talented and doing some amazing things even in their freshman special project. So I think that would be really well received and spur innovation.
I think an interesting thing is when you really look at how did we get to where we are today, that we have all these materials that have been embedded in all of our different products. I think we have this myth that someone defines a problem and a group of scientists invents the solution to that problem. Truth be told, 20, 30, 40 years ago, a couple people met and said, I got tanker trucks of this really inexpensive, cheap stuff. What can we do with it? And so companies will go out and, well, let's make a spoon out of it. Let's make this out of it. And so the availability of a material provided the infrastructure to create all the materials that we use in society. Now we've come up with this need to have it safe, and we say, okay, let's define the materials that make a spoon and ask the scientists to invent a product to meet that. That's not really the way it happened in the first place. It was the availability of the material first, and then the products to commoditize the use of that material. So really, maybe what we have an opportunity to do is to come up with fundamentally sustainable materials and ask the designers of products to use these fundamentally cost-effective, sustainable materials the way it happened the first time around. When 100 years ago when I was a chemist, there was no such thing as industrial design. People weren't going to school to learn about product design. Now there's more people learning about product design than making the molecules. So we have a small subset of molecules that we're designing products to. The way to change the world is to increase the number of materials that products can be built upon that are in fact sustainable. That's the way it happened the first time. So having a prize or something that is asking the designers to reach out with new materials that are sustainable is a way to look at this.
The other thing I would add, I'll just add a little small comment to that, and that is it's really hard to do what you're wanting to do, and that's great, because that's really stimulating for researchers and for science, for the scientific enterprise. I mean, to come up with some new materials with new, better performance properties, inexpensive, that have all the things you want in them, oh my gosh, that's really hard to do. Yeah. Which I think really is great. I mean, that attracts students, that attracts interest from faculty, that gets juices flowing. Hard problem, really? Yeah, it's great.
What's the number?
Number?
What's the number that would get everybody really excited?
Oh, for a prize? What is it, $1 million?
If you can imagine it, it's got to be bigger. Yeah.
Really, really big.
Yeah.
Yes. Is this thing a talking stick by any chance? So that means it's my choice. Rick Coates is the name, and
I don't know where you are.
I am totally excited about the way you're moving this into the classroom, and I'm just wondering, is there a follow-on to move it into the boardrooms and the corporate CEO's office? That is, are you planning to work with your MBA program, maybe a green MBA program, to sort of teach some of this stuff to those folks as well, so that by the time your crop of new chemists that are all gung-ho about green chemistry get to their jobs in these corporations, that there will be some fertile ground for the seeds they sow?
First, many of the companies that you've seen up on the wall here that are participating in this conference and not have actually integrated the 12 principles of green chemistry into their stage gate process of research and development. Companies actually say, as a scientist invent something, as we move it forward in the R&D progress, the 12 principles are actually one of the factors to do. Now, of course, they're having these classes for when they hire new scientists out of college. They're giving them the workshops and the training in green chemistry because they know they're not having it at the universities. So I would argue that industry is ahead of academia in recognizing the value of green chemistry and have integrated it into their work. They're crying in their oatmeal that the students coming out of academia don't know how to meet those needs. But I think we've done a really good job articulating it. And like I said, many of the companies that we've seen listed in icons behind me on the board already have integrated and have massive training programs internal for green chemistry. Yeah.
I also believe that one of my biggest worries as a department head is getting jobs for my students, seeing the students get jobs. And I think the students who have gotten this green chemistry training are more likely to be hired by these companies because the companies are ahead of the curve and want people who have this knowledge already. So I don't know. I kind of agree. I think the companies are doing just fine. That being said, we don't teach much chemistry at all in our business school, it turns out. They don't seem that interested. That being said, Steve Kelley is on our Center for Public Policy, gets involved with the Carlson School people. That's our business school, our Carlson School people. So there is some bleed over in the public policy arena. But I think it's an interesting challenge. How do we get chemistry education over to the business school? I'm not sure how to do that.
The Berkeley Center for Green Chemistry does, one of our assistant directors is from the Haas School, Christine Rosen. What's the name of your program? Sustainable Product Design or Sustainable?
Well, we have a
Clean Tech to Market. Yeah, so we've always felt that the part of what's exciting about green chemistry is that it's interdisciplinary, and so that's built into the efforts.
And then we have in the audience somewhere Professor Andrea Larson that is teaching in the business school at University of Virginia at Darden and at Stanford, and has an entrepreneurship and environment where she brings in many of the speakers from this to be giving lectures in green chemistry. So there are pockets of this happening in business schools. Yeah.
We have one question over here, then we'll just take one more question after that. I know lots of people are putting their hands up, but the panel, you can reach them in the coffee session afterwards, so maybe come up after this session. We'll take two more quick questions.
My name is Dorothy Wigmore. I say about almost the same way as people from Minnesota, and that's because I'm originally from Winnipeg, and that's really where home is, but I'm working across the bay at a place called WorkSafe these days. And as Debbie will can predict, my question is going to be, what about the workers? And that's one of the interdisciplinary things that I've missed in this conversation is occupational health. I actually got into this country, maybe I am a whole person using John's definition. I got into this country as an occupational health specialist in green chemistry. And that's because my training, both as something called a hygienist, where I'm supposed to know about chemicals, and as an ergonomist and a stress specialist, for me, the green chemistry, at least on the chemical end of things, is a really important part of the prevention focus. But in my experience, folks who do green chemistry tend to not think about the people that end up using the different chemicals that people work with. And this was really emphasized for me when I saw the poster that you mentioned about D-limonene. D-limonene is an asthmagen. it should not be in cleaners. And so my question, I guess, is where does occupational health fit into the work that you're doing when you're training people? And how can we think about, we've got participatory ergonomics where workers are involved in getting solutions. How can we have participatory green chemistry so that people, not just the folks in your labs, but the folks who actually work with some of these chemicals in outside labs are very much part of the solution and not seen as part of the problem?
Well, I'm not sure where part of the problem's coming from, but I would argue that 3 of the principles of green chemistry specifically address the people using the materials and the workers on it. And so that the 12 principles cover, one principle talks about the product, and another principle talks about how the product is made and used. And so there's a few of the principles are addressed specifically. And I think it is. Green chemistry is a workers' rights issue. And I think that having green chemistry, you know, the people who are using the material and that are exposed to the potential hazards are in the front line of innovation, and you need their feedback on how to design the next generation of products. If you design a generation of products absent of their input, it isn't going to work. And so they have to be part of this process, not only because of the exposure that they suffer, but also the practical knowledge they have on how to use it and implement it. So if they're not at the design table, shame on the organization that's doing it, that they're losing an opportunity and a responsibility.
Well, a gray area always with green chemistry in my mind is the question of laboratory safety. So laboratory safety is often treated, at least in our department, as a separate issue from green chemistry. And so I can talk a little bit about laboratory safety, which is a huge issue in academic laboratories, and it's something that we're taking very seriously at the University of Minnesota. In fact, we just announced a big partnership with Dow, where we're going to be working with Dow to help learn some of their best practices and bring it into our academic milieu to address issues of laboratory safety. So we actually don't even view it in the lens of green chemistry because it's well, I don't know. I guess it's just as general as green chemistry. We just don't view it that way. It's just a separate item. But it is part of the picture. It shouldn't be a separate item, but it just, organizationally, it is for us. So the Department of Health and Environmental Safety, our safety procedures in our department, all of those issues are handled separately from teaching of green chemistry.
I think it's really important to focus on this. The whole point of green chemistry, in my opinion, is that historically, people have cared about human health and the environment. But we have, over the decades, developed technology where we've become dependent on technologies to mitigate exposure. So we create safety protocols. We wear gloves to protect skin. We wear masks to protect lungs. We wear goggles to protect eyes. And we've done a fairly good, not an excellent, but a fairly good job at working with nasty materials and protecting people. And we've said this is okay. This is what chemistry is. The revolution that is green chemistry is to say that that's not okay. Imagine a future where we're not dependent on exposure controls because the molecules are inherently non-toxic and the exposure is not the issue because the molecule is inherently non-toxic. Right now, that is unimaginable from a technological perspective. It's going to take decades and decades of research. But if we don't agree, that is the dot on the horizon we're all working towards, we're missing the point. That is the dream, is that we don't have to have the safety exposure mitigation devices because the chemists have done their job well and invented safe chemistry all around. That I may not live to see that day, but that's the whole point, is that green chemistry is the next generation of protecting people by intrinsic molecular structure as opposed to engineering exposure controls. That doesn't mean we're dependent on them today. Let's not unplug the filters and go to town here. And we still need to invent better ways of doing that. So it's not saying that that's not important, but the future is not needing them because the molecules are intrinsically non-toxic and safe in the first place.
One last, hopefully quick question.
Ned Woodhouse. I'm a political scientist, and so I don't believe in reasoned persuasion as much as I do in legal force. And so let me take John's question, which I've heard him say 15 years ago, probably, that toxicology isn't taught at chemists. I think one of your examples was you can get a PhD. You might have to learn a foreign language, but you don't have to pass the toxicology test. What would it take as a thought experiment to induce Minnesota and Berkeley to teach toxicology to their chemists? Would you have to have liability on professional chemists? Would you have to have de-accreditation of your department? What would it take?
That wouldn't matter. No, that wouldn't matter to Berkeley.
I've worried about this a lot ever since I heard John talk about this, rail about this a few years ago. And so we actually have a toxicology course that's taught from our School of Public Health. And we have now made it, it's one of the technical electives that counts towards a major. So if a chemistry major can use that course. And so they're taking it outside of chemistry. We do teach toxicology in our green chemistry course. Granted, it's not the entire course. It's not full-blown toxicology, but we do teach it. So we're starting the process. Your question is a tougher one. You want a course that's mandated for the major.
Yeah.
Maybe many courses, I don't know.
That's a real challenge.
But not if the threat is, that the legislative process creates licensure. What happens if in the future some legislative body says, hey, we've got these chemists out there making molecules and not trained. Let's make it a law that they have to take a test. Wouldn't it be better if the field of chemistry heads that off at the pass and says, we got that covered, instead of actually saying, no, we won't do it? We're going to lose that if that happens. So that, I think, is the point. I actually think that is the future. If the chemistry enterprise doesn't take care of it itself, this will happen through a legislative process. I hope that chemistry can get its act together before that happens. Not so sure it will. I hope it does.
To be honest, to be entirely pragmatic about this, I think a more workable approach is to integrate it into existing courses and not try to make a separate course. I think if you try to make a separate course, you're just going to run into a buzzsaw, and you'll never get over it, and and that's exactly where we're at. But if we can get it integrated, get the toxicology concepts, maybe not at the depth that they should be in initially, but get them into the curriculum gradually, piecemeal, through the efforts of people, we'll get it in there, but without the fight. But that's just a political issue.
As like a faculty member, I think part of it is having people build out teaching modules. So I could go to a PChem professor and say, here's a module where you could, how would you introduce this into your course? Here's a little 5-page thing that's going to help you get there. I've benefited from my interactions with Mike and Meg from the School of Public Health and Arlene Bloom, and I'm learning a lot about old toxicology when you were looking for the death of half the population of the things you were studying versus low-dose effects and estrogen disruptors and all of this stuff. And I'm bringing this into the classroom. And the students are learning a little bit about it, but it's not a full-on course. And so what can we build out that has a specific learning goal in mind? My learning goal right now is I want the students to get a taste of this field. But I definitely need help or need some time to build out some of these pieces myself so that the integration is a little bit easier on the faculty member. And so kind of echoing what has been going on before is we need to have more dialogue and communicate, because I suspect a lot of us have these pieces of things that could be put into place pretty easily with not a lot of buzzsaw, as you said.
I suggest, one second, I suggest we carry on the conversation over coffee. If there's one last comment.
I still don't think we heard, I'm sorry, but I don't think you answered the question, and I think it's because we're not in your world that I don't understand why there's a buzzsaw. So this is my naive thing. Who decides curriculum? Is that a national thing? I mean, why is it so hard? I don't get it.
So
Faculty freedom.
By consensus where? Within a university?
Yes.
So Berkeley could decide as Berkeley that in the major...
within a department.
So the Berkeley Department of Chemistry, right. Minnesota Department of Chemistry. So where's the buzzsaw? Tell me about the buzzsaw.
It's because if we say we have to take toxicology, that might mean, they're not going to take second semester PChem. There's something has to give.
Yeah.
You can't add on.
The curriculum is already
hard.
so crowded.
Yeah.
There's such and there's so many vested interests.
Can I end in a provocative?
Yeah.
So I'm going to quickly.
God gets the last word here, and then we're having coffee.
So when I was chair of my chemistry department, we had raging debates about how full the curriculum was. So I said, hey, why don't we have the organic chemistry professor teach PChem this semester? Let's have the analytical chemistry professor teach organic. Let's mix it up. And they go, wait, we can't do that. And I go, wait a minute. We're telling all of our undergraduates you have to master all these classes, but we at the epitome of our profession say that we couldn't teach it. Rationalize that with the curriculum being so full that we can't put something else in. If 85% of what we learned as undergraduates we've forgotten. All right, and so I think that if you really ask people practicing chemists how much of their curriculum is embedded in what they do as a practicing chemist, there's a very small number. It wouldn't be 100%. And if we ask, what did you learn on the job that wasn't in your academic program, that's a big number. And so I think the sacred cow of the curriculum not being changeable needs to be challenged. Now, it's not easy. I'm not saying this is an epic battle of good and evil. This is behavior that's been going on for decades, and it is hard, and there is a buzzsaw. That is real. That barrier is true and real. Should it be there? I would argue no, but that doesn't make it not there. Yeah. Yeah.
Okay, let's take a break.